Here today we will be discussing nuclear magnetic resonance, and first of all, starting with the introduction. Okay, in nuclear magnetic resonance, actually it serves a great resource in determining the structure of an organic compound by revealing the hydrogen and carbon character. Now, how it started? The first thing that we have to know is how it started. It was first revealed that the atoms with even number of proton and neutrons, okay, they are having a kind of diamagnetic character, and they are not having any kind of magnetic field. But the atoms which are having a kind of odd number of okay, so you can see here the nucleus with even number of both proton and neutron experiences no spin, and the nuclei with the odd number of both neutron and proton have an integer spin, means one spin, and the nuclei that have sum of protons and neutrons equal to an odd number have half spin. Okay, and when there is no external applied magnetic field, the nuclear spin orients randomly. However, when there is an applied magnetic field, the nuclei orient themselves with or against the larger applied field. Okay, so it can be even aligned in same direction, or it can even be against. Okay, so using this particular phenomena, the chemist could get a good amount of information regarding molecular structure, particularly unknown. Okay, and they can use it in finding the structural behavior or structural environment of the compound, and finally identify the unknown compound. So let us see this next one. Is that here we have shown that they are in random motion. And here when the nucleus it has a spin. Okay, so it is in same direction, external magnetic field. Alpha is in same direction, and this is beta, which is having opposite spin. Normally the alpha, which is having the same as the external magnetic field, it is having lesser energy, but when it absorbs the radiation, it jumps to the higher level and it flips the nuclear spin. Okay, there is a flip from upspin to downspin. Okay, and this particular energy gap, okay, it will vary. It can vary depending on the applied magnetic field. If the applied magnetic field is very less, suppose this is the value, okay, this is the 0 mark, and so as we go in the right hand side, we see that the applied magnetic field increases. If the applied magnetic field is this much, the energy gap is this much. Okay, and if the applied magnetic field is this much, okay, particularly here, the energy gap increases. So this depends on the applied magnetic field. Now, to study any molecule, supposing the NMR of the molecule, or you can say the number of hydrogen or protons in the molecule, we have to take a reference where we have taken this particular gap. Even though it is having a certain amount of gap, we will take it as equivalent to 0. So that particular compound is called reference compound, and normally we take it as tetramethyl silane. Okay, tetramethyl silane means SiCH3 4 times. So here we have same type of hydrogen same environmental equivalent hydrogen, same environment hydrogen with same equivalent hydrogen 12. Okay, therefore it is very easier to study the molecule in reference with the TMS. So here we see this is the TMS, and accordingly we have found two different peaks. So this is quite close to TMS and this is quite away from TMS. Now what we next see is this. What are this? This is intensity, means the number of the height of the peak will tell you the number of hydrogen involved here, and this is what is del. Okay, del is what? Del is the frequency. So it is 0 and this side it is increasing as we go in the left hand side. So we have certain terms like upfield and downfield. We'll see that. Okay, so here what we have seen is okay. So before the magnetic field is applied, we see it is totally random. Once the magnetic field has been applied, okay, it will align in one direction. It can align even upstream and it can align in opposite to this applied magnetic field, that is downfield. Okay, so this particular energy gap also we have discussed. Okay, now what we have is the reference compound, tetramethylsilane. Okay, and it has been taken as 0. What is delta? That we have to know. So here the reference compound is at 0 position on the very left of the spectrum. Now what is delta? Delta is the distance downfield from TMS divided by operational frequency of the spectrometer. Okay, that is parts per million in this unit. It is hertz by megahertz. Okay, so here what we have, it is having 1 by million. It is hertz, it is megahertz. So what we have is, it is 1 by mega, means we can say it is 1 10 to the power 6. So it is therefore parts per million, 1 part by 1 million. Okay. So this is what is the meaning of parts per million, distance downfield from TMS. Okay, so what is the distance? So that is what is delta. So here if you see this particular graph, so this is TMS, and what is the distance from the TMS is, okay, so what is the distance? So this is less distance, so it is delta is less, and this is far away from the TMS, so it is having more delta. So therefore what we can say is, next what we have is so what is upfield and downfield, that we see in this graph. Okay, what is upfield? Upfield is the extreme right hand side. So when do we get in that direction the peaks? We will get the peaks when the electrons when the protons are in electron dense environment. So when it is electron in an electron dense environment, it is much shielded, and large amount of electrons are covering it, shielding it, and therefore will require low frequency to resonate the nucleus or to flip the nucleus from upfield to downfield. Okay, downspin, upspin to downspin. So therefore the del is in the smaller side. This is called upfield. Upfield means farther towards the right hand side of the spectrum. Now, what is downfield? Downfield is when the proton is an environment where the electron is, electrons are not in its, surrounding. It is less shielded, or you can say it is de-shielded. Supposing the hydrogen is bonded to oxygen, so oxygen is having more electronegativity, so oxygen will pull the electrons towards it, and accordingly the hydrogen that will be left behind will be de-shielded, means the electrons will not be there to cover it. So accordingly what we will get is that it will require lots of energy to resonate it, and therefore del E is larger, and when del E will be larger, that del E will be larger, the delta value will be larger, and therefore it is in the higher frequency and towards the left hand side. So this particular thing is, we call it as downfield, okay, because it is de-shielded. De-shielded means downfield. Okay, so let us see some few more terms. Now you have gone into this part, chemical shift. What is chemical shift? This del E value is nothing but chemical shift. Okay, so chemical shift, this particular value can change, okay, depending on the environment. If it is in the electronegative environment, electronegative atoms environment, then del E is chemical shift is more towards the downfield side. Okay, so that is what is here it is mentioned. So electronegativity defines as the tendency of the atom to pull the electrons towards it. Therefore electronegative atoms removes the electron density. So we have already discussed this part. So del E, and the higher chemical shift, more higher will be the del E required, and higher will be the chemical shift. Okay, so del is the chemical shift, or delta E is the chemical shift. So let us see one or two values. So here what you can find from the interpretation of, so first thing, depending on the number of peaks, we can understand. Supposing in this one it is reference well understood. In this particular spectrum, what we see is that there are two different peaks. So these two different peaks, first interpretation that will be, is we have in the molecule hydrogen of two different environments, or two different chemically equivalent protons are there. Okay, so that is what is first information. Second information that will come is, so what is the position? So based on this particular graph, if you see the position, so there are two types of position. Here one is closed, so it is in the upfield, so it is much shielded by the electrons, and it is much de-shielded by the electrons, because of which it is requiring more energy to flip it, to flip the nuclei from upstream to downstream. This is the second environment second information that we get. Okay, position. And next is, what is the number of hydrogen present here? So here again what we can understand is that what is the number of hydrogen. Since the height of this peak, or the area in this triangular peaks are almost same, so we can conclude that the number of hydrogen present here and present here are same. Okay, are same. So that is one other information that we get out of it. So supposing, let us take this example. Here what you see is there are CH3Br. Now what will be the comparison? This H are bonded to this carbon, and this carbon is the same carbon is bonded to bromine. So this bromine is having electronegativity, so this hydrogen becomes de-shielded, and therefore the energy required is more. Supposing this particular hydrogen and this particular hydrogen are having different environment. What is the reason? This halogen is bonded to this particular carbon and not to this particular carbon. So therefore it is less deshielded. So therefore the energy required is lesser compared to this, and it is further less and it is further less. Okay. So next we will go for spin coupling and magnetic anisotropy. That also we have a different topic. So we will discuss.